10-1. Sequences as functions. Oh. I plugged it in after I opened it, so let me reopen it. I think that's what the problem is. There we go. A sequence is a list of numbers. I mean, we could stop there. It's a list of numbers. And then we go on in a particular order or pattern. Usually, it doesn't have to be. Each number in a sequence is called a term. Each number in a sequence is called a term. So 1, 2, 3, 4, that's a sequence of numbers. So 1 is the first term, 2 is the second term in this sequence, 3 is the third term, and so on. The first term is symbolized by a sub 1. So in the little sequence that I did here, that's a sub 1, this is a sub 2, but you could go 2, 4, 6, 8, keep on going like this. This is still a sub 1, that's a sub 2, and so on, a sub 3. Term 1, term 2, term 3. Many sequences have patterns. Both of them that I gave has a pattern. A sequence may be a finite sequence. It ends. Or an infinite sequence without end. I wrote 2 infinite sequences. I know it's infinite because I put comma, dot, dot, dot. That means infinite. Now if I just wrote 2, 4, 6, 8, like that, that's a finite sequence. That stops without the comma, dot, dot, dot. So finite, infinite. That's the difference. Anything down below that? Oh yeah, good thing I looked. I guess it shows it right there. An example. If I go full page, I would have seen that. Let's go full page so I can see the entire notes. Or maybe not. Try it again. There we go. So negative 2, 0, 2, 4, 6, that's finite. A sub 1, a sub 2. And then here's infinite over there, just like I demonstrated. Now we get into the specific sequences and their names. First of all, we have an arithmetic sequence. An arithmetic sequence is a sequence in which each term after the first is found by adding a constant, called the common difference. We label it letter D, to the previous term. Now what does that mean? Well, let's look at an example. Determine whether each sequence is arithmetic, yes or no. And I actually want to grab a calculator. I don't know if I need it on this first one, but I'm probably going to use it eventually anyway. We need to find out if these are arithmetic, which means we've added something to the first term, added the same thing to the second term, added the same thing to the third term to get the next one. So if you pick any 2 consecutive ones, like pick a sub 1 and maybe a sub 2, the most convenient. Take a sub 2 minus a sub 1. So like negative 2 minus negative 8. So take the second one minus the first one to see what we're adding, if we are actually adding. So if we take negative 2 minus negative 8, we get 6. So we might be adding 6. You add 6 to get negative 2. Now if it's truly arithmetic, we added 6 every single time. So is negative 2 plus 6 4? It is, isn't it? Is 4 plus 6 10? Yes. This is a good indication that this is arithmetic. So we're going to say yes. Now if I take negative 8 minus negative 3, negative 8 minus negative 3, I get negative 5. So in other words, is negative 3 minus 5 negative 8? Yeah, that's what we found. Is negative 8 minus 5 negative 13? It is, isn't it? Is negative 13 minus 5 negative 23? No. This is not arithmetic. It sure started out like it. It looked like we were good to go. It looked like we were going to get arithmetic. But that last one ruined it. So it is not arithmetic, even though it started out that way. Find the next 4 terms of each arithmetic sequence and then graph the sequence. It looks like we're adding 2. Negative 6 minus negative 8. That's actually 2. So if I add 2, find the next 4 terms. So negative 4 plus 2 is negative 2, 0, and 2. That says graph them. It has a two-dimensional graph. So we're going to have to figure out how we're going to get the other numbers. We're going to make these numbers the y's. Let's go 1, 2, 3. This is the 4th term, 5th term, 6th term. So we have 6 terms. We'll make the 1 through 6 the x's. We'll make the results the y's. So we have 1, negative 8. 1, 2, 3, 4, 5, 6, 7, 8 down here. 2 is negative 6. 3 is negative 4. 4 must be negative 2. 5 is 0. And 6 is 2. Now we don't play connect the dots because we don't have any of the values in between. We only have these values. So when you graph a sequence of numbers, you just get dots. We don't play connect the dots like we do with a function because it's only at the integers. However, whoever made this slide, I like it, I like this slide. What did this teacher want you to see about this graph? What do you notice about those dots? They're all spaced the same. I like it. I'm looking for a different answer though. What kind of graph is it? If we were to play connect the dots. It's a line, right? Linear. Arithmetic sequences is really a linear function, kind of, except we don't have any of the values in between. So this is really linear. They line up. Geometric sequence. All right, so arithmetic, you add to the previous term to get the next one. You always add the same thing. A geometric sequence, you multiply to get the next term. And geometric sequence is a sequence in which each term after the first is found by multiplying a non-zero. Don't multiply by 0. That's not geometric. You'd get all zeros. Non-zero constant called the common ratio, we label that R, to the previous term. Determine whether each sequence is geometric, right? Yes or no. So here we have what might be a geometric sequence. To find out if that's true, the R is 30 now divided by 19. That's how you find out what you multiplied by. You divide to find out what you multiplied by. So if you take the second one divided by the first, 30 divided by 19 is some decimal. It's not nice. So that ends up being 1.5789, keep on going. Well, is 41 divided by 30, does that give you the same thing? 41 divided by 30. No, it does not. That's 1.366. So this is not arithmetic. We're not multiplying by the same thing. There might be a pattern there, but it's not geometric. We know that. We just found that out. All right, how about this one? 20 over 8. I can reduce that to 10�4, 5 halves. That reduces to 5 halves. How about the second one? 50 divided by 20. That's, well, if I divide by 10, that's 5 halves. Looking good so far. How about the last one? 125 over 50. I can divide both of those by 25. Oh yeah, that'd be 5 halves. This is a yes. Every time we're multiplying by 2.5, 2.5, 2.5, 2.5. That's geometric. Find the next 3 terms of each geometric sequence. The next 3. What you're going to find out is geometric sequences increase very quickly. Very quickly. So let's take 15 divided by 10. Now we're told this is a geometric sequence. So the R is 1.5. That's also 3 halves, by the way, if you want to know what the fraction is. So we're going to take 22.5. We're going to multiply by 1.5. So our next term is 33.75. So that's the first one. It says find the next 3. And then we can just hit times 1.5. So 50 and some change. 50.625. And then one more. Times 1.5. 75.9375. So we're going to graph this. We're going to do the same thing. We need an x and a y. So 1, 2, 3, 4, 5. Those are the x's. And then we'll make the y's the values. But we have to go all the way up to 75. Should we go by 5, 10, 50, 20, 25, 30, 35, 40, 45, 50, 50? Yeah, that'll work. So let's go by 5s. So we'll go by 5s. Let's just make that note. So 1 is 33. 5, 10, 50, 20, 25, 30. That'd be 35. 33 has got to be somewhere about there. That's 30, 35, 40, 45, 50. Just slightly above 50, right, for 2. And then 3 is 75. 55, 60, 65, 70, 75, right there. Oh, did I skip some? Oh. What am I doing? Hey, back off, back off. Oh my goodness. I gotta back up all the way to there. 1, 2, 3, 4, 5, 6. I was like, wait a minute, this isn't working out at all. All right, that was not smart. 5 is down here again. Let's go 10. 1 is 10. 2 is 15. 5, 10, 15. This is looking better already. 5, 10, 15, 20, 22 and a half, about right there. 5, 10, 15, 20, 25, 33.75, about right there. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, about right there. And that's 50, 55, 60, 65, 70, 75, and a little bit more is right there. What you're kind of supposed to take out of this is not linear. It's not increasing at the same amount. Like a line increases the same amount all the time. That's what rise over run is all about. The rise over run is exactly the same every single time. That's the whole point of slope. Rise over run, rise over run, rise over run, rise over run. That should all be the same for a line. But this one, the rise over run, is not the same for each. So that little rise over run, that's bigger, that's a bigger one, that's a bigger one, that's a bigger one. That's not linear. It's something else. So geometric increases more and more and more and more and more. It increases very quickly once you graph it correctly, once you don't do stupid stuff like I just did. Determine whether each sequence is arithmetic, geometric, or neither. Explain by stating the difference or common ratio, the D or the R. So tell the D or tell the R, arithmetic or geometric. Let's see, if we take 16 plus 8, that's 24. 24 plus 8 is 32. This is not arithmetic. What about 24 over 16? That's 6/4, that's 3 halves. 36 over 24, that's 6/4, that's 3 halves. How about 54 over 36? What goes into both of those? 9 does?
Yeah.
5/4? Wait. What's that now? It's not geometric, is it? Because that would be 6/4, that's 3 halves. 36 over 24, that'd be 6. What goes into both those? 6 does. 6/4, that's 3 halves. Does this one ruin it?
No. Divide by 18.
What's that?
Divide by 18 is 3 halves.
This is still 3 halves? Oh, okay. Well, there you go. Oh, yeah, divide by 18. Yeah, 3 halves. Geometric. Geometric, the R is 3 halves. So that's what they want out of this one. Let's see, if I add 3, I get 4. Add 3, I get 7. This is not arithmetic. 4 over 1 is 4. 9 over 4 is not 4. Neither. (23 minus 6 is 17. You can do that by taking, look at this. 17 minus 23. Remember, you take the second one minus the first one. That means you're adding -6 or subtracting 6. That's the same thing. That is, when you minus, that's the same as adding. You just add the opposite. So -6, -6, -6. This is arithmetic. So that's the first answer they want you to give, where D, the difference between the two, is -6. Be careful with that. The D is -6 on that, not 6. If you're adding 6, it's 6. If you're adding -6, it's -6. Just take the second one minus the first. During their routine, a marching band marches in rows. There is one performer in the first row, 3 performers in the next row, 5 in the third row. This pattern continues for the rest of the rows. Help the director determine how many performers will be in the 14th row during the routine. So we have a couple choices. One choice, keep adding 2, right? Until you get to the 14th one. That would be a horrible way to do this one, especially if I asked you how many would be in the 100th row. You don't want to sit there for 5 minutes and write it all out. There's a much easier way. Let's list a couple more. 7, 9, maybe one more, 11. I don't want to go to the 14th. I don't want you to do that. Much easier way. Isn't this 1 plus 2? This is 1 plus 4. 1 plus what? 6. 1 plus 8, right? So we can take 1 plus something times 2, because this is 1 times 2, 2 times 2, 3 times 2, 4 times 2. How many 2's do we need to get to the 14th term, though? Be careful. It's not what you think. How many 2's would we need for the last one, for the 14th? Think of it this way. For the second term, we take 1 times 2. For the third term, we take 2 times 2. For the fourth term, we take 3 times 2. So what about the 14th term? What times 2? You don't know? How many? Okay, let's try it again. For the second term, we take 1 times 2. For the third term, we take 2 times 2. For the fourth term, we take 3 times 2. What about the 14th? What times 2?
13.
13, right? It's lagging behind by 1. So for the second term, it's 1 times 2. For the third term, it's 3 times 2. And it's lagging behind because for the first term, you don't add anything. That's just the first term. So it's going to lag behind by 1 because you don't add anything to the first term. So 13 times 2. That's 26. So the last one, the 14th we want, there should be 27 people in that row. All right, well, you wouldn't do this. 13, 15, 17, 19, 21, 23. I'm writing all over the place. 25, 27, that should be the 14th. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right there, 27. So we lag behind by 1. Glad you had time to stop and get that. That doesn't ever bug teachers at all. Doesn't bother us a bit. That's easy. I don't care. Put everything away except for piece of paper, pencil, and calculator. I have no idea what that's for. Don't worry about it. If it's crucial, we'll do it tomorrow. There's your assignment. Does it have? I think it has the book stuff on there. So just do those problems, and you should be good. There will be no speed dating on my watch.